The next current circuit building block that we're going to introduce is resistance and a quantity called resistivity. Resistivity and resistance. Resistance. Turns out that it's much easier to measure the potential difference, right, going back to V, between 2 points than it is to measure the electric field inside a conductor, right? So we started with this concept of electric field because it made more sense from the platform that we were jumping off of from mechanics. We understood about potential energy and gravitational field and all that, but now moving on to circuits and just electromagnetism in general, actually, it's easier to work with potential. And we, of course, know that the two quantities are related. The electric field points from high potential to low potential, just the same as gravitational field points from high gravitational potential to low gravitational potential, right? V is just the potential energy per unit charge, right? And what we want to know now is as these things flow from a higher potential to a lower potential, right, V1 to V2, what quantity governs how fast that happens, or, like what governs that process exactly, right? So in kind of the same way we're talking about current of being obstructed, right, and it would otherwise travel infinitely fast over a certain period of time. What governs this process of going from high potential to low potential, and what slows it down? How can we quantify this? So introducing a quantity called resistance, which is what it sounds like. So resistance is usually denoted with an R, capital R, and it's equal to, R is equal to rho, but in this case it's not density, times L divided by A for a given material. This is a quantity called the resistivity of a material. Resistivity of a material. L is the length of the material. So imagine a wire, right? Or just like a metal bar, right? And then A is the cross-sectional area. So for lots of materials, the resistivity is the same across a large range of potential differences that's applied to a material, meaning that if we had, that bar that we were talking about before, where we had current going and you had some large high potential here, right, and some lower potential here, lower, higher, and then there would be an electric field pointing this way, right? And so then charges would be motivated to move, right? If we're talking about the electrons, then they would be motivated to move this way. Current talks about the positive charges, so I'm going to retreat back to the positive charges in the material, which you can consider as anti-electrons, or the holes that electrons would occupy. If you're unfamiliar with any of these concepts, just imagine positive charges. It literally works just fine. But that they would be motivated to move to the right along the electric field, and we would say that that's the direction of current, right? And so in the case where the resistivity of this material is the same regardless of this potential difference, right? Regardless of if this is like super duper high compared to the right side, or not very much high, right? So think how steep the hill is, how steep the electric hill is, and the charges are rolling downhill. So no matter how steep this hill is, electrical hill, most materials act relatively the same. and that is said to be that they are ohmic. If their resistivity is about the same regardless of the potential difference connected to either end of them, then a material is ohmic. And if that's the case, then the following relationship between voltage, current, and resistance applies. And this is a big one, so I'm going to write it nice and big. V equals I R. Big one. Here we go. So this relationship is usually called Ohm's law, right? Because we built up to it talking about things that are ohmic. But I'm going to pull out a subtlety here. It actually applies to any conductor, not just when R is constant. Thus, we can say when R is constant that it obeys Ohm's law. But because V equals IR, this whole equation has no fancy name in general for all conductors, regardless of if this R is constant or not, then people often just call it by its case-specific name for the case when R is constant. So by analogy, it's kind of like calling all fizzy, sugary drinks Coca-Cola or Coke, because we never really bothered to create a word for soda, right? So it's fine, it works. You can call all soda Coke. People would know what you're talking about, but there really should just be a generic term for soda, a generic term for this relationship instead of the quote-unquote brand name ohmic that applies to only one version of that equation. Anyhow, perfectly fine to refer to that as Ohm's law. It is often referred to as Ohm's law. The SI unit of resistance is the ohm, and it's denoted with the symbol omega. This is a capital omega, which is equal to a volt per amp. Yeah. Resistance, SI units. Boom. So at this point, I'd like to introduce the fluid flow analogy for circuits. It's really, really useful. We've already kind of pulled on gravitational analogy. We're going to introduce just how fluid flows downhill to help us understand circuits, because it's a really great analogy. So in this analogy, the water analogy for circuits, we think about water flowing downhill. You can think about it in flowing in a pipe, right? The reason the water flows downhill is because of the height difference. If you had a pipe completely horizontal, flat, across flat land, it doesn't matter how much of a reservoir of water you had on the left or the right, water would not flow one way or the other on the pipe. It has no reason to. Water flows downhill because it contains mass, and it's affected by the gravitational field that it's in, and that scales with distance, right? Elevation. So that's the reason that water flows downhill. In the analogy to electrical circuits, this is analogous to the voltage in electric circuit. Charges flow from high electric potential to low electric potential, like from the high potential side of a battery, the positive terminal of a battery, around the circuit to the low potential side of the battery, the negative terminal of a battery. And the rate at which the water flows downhill in our pipe is called the current, and we use the same word for that, fluid flow in like a river, right? It's the current. And that applies just the same for electric circuits. Current of a river can be thought of as water molecules per second passing a given point in the river. Current of an electric circuit is charges per second passing a given point, right? Same concept. Given a water pipe aimed downhill, the water current facilitating the pipe is determined, or you might say restricted, or resisted by the diameter of the pipe. A really large diameter pipe facilitates lots of water molecules per second passing by any given point along the pipe. A smaller diameter pipe resists the current of water more. And in our analogy, the diameter of the pipe, you might guess, is like the resistance of the conductor that is facilitating electrical current flowing through it. So keep this analogy in mind, right? Keep this analogy in mind where you have like some reservoir of water up here and you have like a pipe that has the ability to transport water from uphill to downhill. The width of the pipe is kind of like the resistance. The height difference, I should use different colors from now on for, all right, we're going to use red for voltage. Try to hold me to it. So the height difference here, that's the voltage. The, let's see, we'll use blue for blue for current, huh? The width of the pipe is the resistance, and the flow of the water is the current.